So my talk is Gels, Evolution, and Practice, and it's not a proper history of the use of gels in conservation, but kind of my history with gels in my own private practice. And one thing I want to mention before that is never follow Richard on a talk. So I'm very grateful I had last night to kind of take out some little things in my talk that weren't, after his talk. So anyway, I would highly recommend, if you have any chance in scheduling a talk in the same conference as Richard, to go on the day after. So anyway, I'll be spending some time talking about carbopolyamine solvent gels, which I use less and less, and I think Richard uses less and less because we've got such better tools. But as we saw this morning, they're still used quite a bit. So one of the things I wanted to do with this paper was to talk about kind of the research I've done on how carbopol gels are formulated from the point of view of a practicing conservator. The utility of gels in conservation can really be traced back to Helmut Ruhmann's ammonia wax paste emulsion. Oh, probably push a button. And what I found really amazing is in the text he talks about what the special advantages are. It opens up certain films that do not respond to the usual solvents. It stays put, does not run or spread, so that the cleaning operation can be confined to desirable minute spots. Its action can be modified by the concentration of the mixture and the thickness of application and length of time it is left to act. True today as it was when written. And the ammonia wax paste was a suspension of, there we go, ammonium carbonate solution into the dispersed phase into a mixture of wax and white spirits or turpentine to kind of form the continuous phase, and just by mechanical action and the cooling of the wax part that the aqueous phase was emulsified. So things remained relatively quiet on the gels front from the 60s when the book was published to the 80s when Richard at Winterthur began using and introducing a number of gelled cleaning systems to the conservation field at large. And then in the 2000s, I began developing the modular cleaning program as a means to kind of systemize and organize Richard's insights and innovations into a system for paintings and then by extension other practices. And kind of after that initial aqueous formulation of the MCP, I started incorporating the idea of solvents and solvent gels into the system as well. So originally, when people asked me what the talk was going to be, it was like, you're going to talk about the MCP. No, I'm going to talk about practical things. So of course I'm going to talk about the MCP. And then, it all goes back to, in the 80s, Richard, the book, the archetype book. So I'm not going to talk about the modular cleaning program, obviously. For those unfamiliar with the modular cleaning program, which I hope all of you are familiar with, it's a computer program built in FileMaker Pro, and the idea is that the program assists the conservator in kind of conceptualizing how you can mix and match, put together cleaning solutions quickly, and how you can kind of view what kind of changes can be made to a system to make it more effective, more tailored to the cleaning problem at hand. One of the things I worked on very hard in formulating this is that all the recipes are based on physical constants. So recipes are based on molecular weight, acid dissociation constants, Hansen solubility parameters, that sort of thing, rather than it being Richard's recipe or my recipe. And then further, it's an approach to customizing a cleaning solution and, and putting concentrates in bottles that you can mix and match and come up with a prototype cleaning systems very quickly. And the one thing I always stress is that the computer never makes a suggestion on what you should do next. It's always up to us as the conservator to apply our experience and our eyes and our hands to the problem and let the computer do calculations involving acid dissociation constants and that sort of thing. So, solvent gels. So these, as we heard earlier today, these are built from carbopol, a polyacrylic acid, and an organic amine. And then there's always a small amount of water necessary to form the gelation reaction, the interaction between the amine and the carbopol. So you'll see it consists of a long carbon backbone with alternating carboxylic acids on it. So the trick to, can you make that, there's a little play button on that, or does it not work? If you move a cursor over it. There we go. Oh. It's just a short little animation. Okay. Trust me, if this were playing, it would show that carbopol molecule. This is basically how it comes out of the container. When you make it happy, relaxed in the solution it's in, whether it's water or solvents, that molecule just unfurls and becomes larger and larger, and we kind of have that spaghetti, colander full of spaghetti model of gelation happening. So, in the really early days of working with solvent gels, maybe Richard had recipes, but I didn't. So the way you made a solvent gel is you mix carbopol and the amine and the solvent and some water, and if it didn't gel, you added more solvent or more amine or more water, and you either got a gel or you got a little lump of stuff at the bottom of the beaker and started over again. So I was working on a painting that had a natural resin varnish and a sensitive oil paint below, and typical solvent systems, you know, just weren't getting there. It was either over cleaning the paint below or not affecting the varnish. So I wanted to use a gelled system, and a xylene gel worked, you know, turned out to be the answer. So I mixed the gel this way, a little solvent, a little this, a little that. Finally got a really nice gel, and it cleaned the painting beautifully. And I cleaned it, cleared it, all the things you're supposed to do, and came back when all the clearing agents had evaporated, and the painting absolutely reeked of ethylamine C12. And that led me to some realizations. First of all, you have to figure out the problem, have to engineer a solution, as Richard was talking about. So fortunately, the ethylamine C12 is also a cationic surfactant. So I realized that to get this residue off the surface that I assume had kind of, there was an excess of amine to the carbopol, so any of the free acid groups on the surface of that oil paint formed the same kind of adduct of the amine to the acid group as it had on the carbopol gel. And I realized that, okay, so we take a little vinegar, a little acetic acid and water, roll that on the surface, it protonates the amine, turns it into a surfactant, and it just comes off in a sudsy foam that can be rinsed and cleared. So that all worked out well. But it led me to this idea that we really have to think about carbopol-based solvent gels as a chemical problem and not just black magic where we mix things together until it either falls apart or turns into a proper free gel. So my rules are we never want to have more than the stoichiometric amount of amine to the carbopol. So we want to have up to one ethylamine or armine molecule per acid group on the carbopol, but no more. We don't want to have free amine floating around that can possibly interact with the paint surface. And then the other one was, okay, so we can do that. That's a simple calculation. There also has to be a chemical reason why a certain amount of water is necessary, and we can determine that. So we have carbopol resin and three bases we can use for solvent gels. Ethylamine C25 for the highest polarity solvent gels, ethylamine C12 for low and mid polarity gels, and for very low polarity gels we can use armine 2C. The bad news is that at the moment you can't get armine 2C, but other than that it's a great system. So ethylamine C25, you've probably all seen this diagram before. It's a 12 carbon chain with 25 ethoxylate groups and 2 branches coming off the nitrogen. A C12 is just one ethoxylate group, which turns out to be an alcohol group on the end of the amine, and still that 12 carbon chain. And the unavailable but really cool one is armine 2C, which is 2 C12 carbon chains on a secondary amine. So with the Armine 2C, because it's not available, I like to talk about it a lot. So you can all be, wish you could get a sample of this stuff, which apparently you can't anymore. But I'm hopeful that, maybe sometime somebody in China will start making it, we can get it again. Actually, I was told by AkzoNobel US that it's not unavailable. That's not true. All you have to do is order a train, literally a train load full, and they'll make it up for you. So unfortunately, it's not that good a gel. So I always think of this low polarity system of the Armine 2Cs studded around this carbopol polymer as like a fuzzy caterpillar. We have all these hairs of that low polarity, the C12 chains, kind of really masking that high polarity carbopol molecule. So it really goes into a very low polarity environment. So the question then is, okay, we know how much amine to add per carbopol. 2 grams carbopol is a given amount of amine. What about the water? We need the water to make this interaction happen. So what I did one day is, or over a couple days, sat on the stairs in my studio, held the beaker between my feet, and carefully measured how much water while stirring until I got a really nice gel, nice consistency, crystal clear. And, then measured how much water it is, did a little math to come up with how many moles of water were added. And it turns out that for the amine linkage to the acid group, it takes 2 molecules of water. So now we have a recipe for making gel thickened with Armine 2C. We can take for a given amount of carbopol how much Armine 2C to add and how much water. Forget that picture. For the ethylamine C12, same thing, and it turns out it takes 4 molecules of water for each linkage. So we have 2 molecules of water between the amine group and the, this is just by conjecture, this is, seat of your pants empirical chemistry, but it makes sense. We need 2 molecules of water to go between the amine and the carboxylic acid group, and each of those pendant alcohol groups seems to want a water molecule as well. It was a little harder to determine the exact amount with the C25, but it seems reasonable to say it's 17 molecules of water per linkage, 2 again between the amine and the carboxylic acid, and then 1 each for the each molecule on the ethoxylate chain. So this is represented in the MCP program that I'm not going to talk about. The lower half is the gel formation. It's the carbopol, the amine, and the water necessary to make that gel, and that's all calculated out. And the top part is the solvents that go into that gel. Unfortunately, what I haven't worked out yet is to have the MCP say, if I want to gel these 2 solvents or 3 solvents, what amine do I use? Possibly a combination of 2 amines together to make the best solubility of the carbopol into that solvent system. Haven't worked it out yet, but maybe one day. Most of these things I say I'm going to work it out in the next couple of months, and by 2 or 3 years later it still hasn't been worked out. So this is how, in the MCP program, we model a set of solvent gels. Any 2 adjacent gels can be mixed with each other and not precipitate. If you try to mix a acetone gel with a really low polarity gel, it just falls out of solution. So the steps along the way allow you to mix and come up with any concentration. And this is admittedly just aliphatic, aromatic, hydrogen bonding, and dipolar interactions on that chart. It doesn't include things like methylpyrrolidinone and all the other things you can put into solvent gels, but this is how I represent it in the modular cleaning program. With all new systems, there are new techniques of application, and the idea of using the white nylon bristle brush, again from Richard, is that you can put the gel on in a nice glop and kind of work through it and see if something's coming up by contrast with a white bristle. So you can tell if paint's coming up, which is obviously a bad thing, or if varnish is coming up. If you just put the gel on the surface, you can't tell if the discolored material is just rising up into the gel or if it's actually not going anywhere. So agitating it gently with a brush. More importantly is the clearance issue. The research at the Getty publication on gels and conservation or something showed that with proper clearance, only a very low amount of amine and carbopol are left behind. But the trick is this proper clearance. So the first thing you do is wipe away the excess gel from the surface, either with a dry swab or a slightly dampened swab, and you kind of counter roll as you're picking it up and just physically remove it from the surface. Then more importantly is to clear that material, to rinse it away. And what I found, you usually want to use a lower polarity solvent than the one you've made the gel with. So you back down the polarity and you want to make sure that rinse is going to remove that gel effectively. And the way I've found the easiest way to determine this is you put a little bit of the solvent mixture or solvent in a little tiny cup. You take some of the gel onto a shiny little spatula, put it in the solvent, and if it forms a white haze over the front, obviously that gel is not compatible with the clearance solvent you were thinking about using. If it passes that test, then you just kind of mush up the gel into the little cup of solvent, and if it disperses uniformly and isn't stringy or anything, you know you've got a proper polarity system to clear that gel away. And you always work out the clearance before you put anything on the surface. So, as I said, I find myself using carbopol gels or solvent gels much less frequently, but they're still a good tool in our toolkit, as Richard says. Talking about aqueous gels. Oh, there's the solvent gel clearance. Aqueous gels. So we can make many different ways of formulating an aqueous gel. I obviously prefer to formulate them with a modular cleaning program, but you can make aqueous gels any way you like, or aqueous cleaning systems. And an aqueous cleaning system can be used as a free liquid, but it can also be gelled. It can become the continuous phase in an emulsion, and then it can become the dispersed phase in a low polarity emulsion system. So one of the things I like by being able to tailor the aqueous component, you can then incorporate that material into a Pemulin or xanthan emulsion or into a KSG gelled system emulsion. So this is using the MCP to formulate a resin soap system using deoxycholic acid, the resin soap, citric acid as a chelating agent, and a bicene buffer to hold the pH at 8.5. And here we're gelling that system with xanthan gum. So kind of over the years, we've gone from Richard's, kind of started using HPMC or methyl cellulose to gel these systems, and then Pemulin and now xanthan gum. Each has its place in our toolbox. The HPMC, basically just gels the aqueous phase, but it's great because it's neutral for putting enzymes and that sort of thing, which we've heard about as well. So you can put the enzymes into the HPMC gel. These are biological buffers that we build these things with, so you can make a quick and easy carrier for the enzyme. But there's something special that happens when we gel a system with a polyacrylic acid, either carbopol or Pemulin, just for the aqueous phase. But the advantage to using xanthan gum is that even though it's a anionic material, it basically doesn't change the pH of the solution you're putting it in if it's a good quality material. And Pemulin, because it's a polyacrylic acid, you do have to set the pH. And I've written 3 articles now on how to set the pH of Pemulin. At least 2 out of 3 are wrong. They don't. Yes, a special electrode pH meter for measuring gels, I presume gives good readings. I found a pH indicator dye added to the gel, obviously not what you're going to put on the surface of the artwork, gives a colorimetric indication, and you can just compare it to a pH of known value. So both xanthan and Pemulin are polymeric emulsion stabilizers as well. And for reasons that are in the paper, the published paper, I won't go into that here, but we can make an emulsion kind of first time, every time. You take xanthan or Pemulin, add your aqueous components, adjust the conductivity, the pH, add chelating agents because they're very tolerant of ionic material, and then you just squirt in solvent and you have a non-water miscible solvent, and you have an emulsion. Typical solvents for this are benzyl alcohol, kind of the #1 go-to, xylene, or mineral or white spirits. Benzyl alcohol, we have something that's aromatic and alcoholic that goes in. Xylene, we have just aromaticity, and mineral spirits or white spirits, we have pretty much just aliphatic material to go into these emulsion systems. So to make a PEMulin aqueous gel, again with the MCP system that I'm not going to talk about, you take 5 grams or 5 mils of the stock PEMulin gel, which is at 2%. We want a 1% final working system. We scoop it out into a little cup on our stirrer, add our MCP components, give it a quick stir with a spatula to kind of break up the big lumps, stir it for a while, and we get a nice, even, homogeneous aqueous gel, which we can use as is. Or we can stir in some solvent, again, run it on the little stirrer, and we get this beautiful emulsion, first time, every time. Great. Sorry. So here, again, is a 6.5 system built with 6.5 buffer, citrate, and xanthan gum, and then adding essentially 10% of benzyl alcohol into that system to make an emulsion system, a xanthan-based emulsion system. So similar to what we saw with the PEMulin. So the nice thing about all this is these emulsions can be cleared with pH-adjusted water. So that's simply a mixture of water, acetic acid, and ammonium hydroxide. All these materials are volatile. You don't have to worry about residue after you clear the gel away. This just evaporates away and you're left with nothing left behind as a residue on the surface from the clearing system. So we have something really amazing here. Again, going back to Richard's thing about green chemistry, better for the environment. We have a system that can actually remove we can remove something that would normally be soluble only in solvents with an emulsion system. And then even better, we can clear that with water. So we're really minimizing the solvent. We're minimizing the amount of solvent released into air because that solvent is entrapped in the emulsion, the dispersed phase of the emulsion. And we can get it off with, we can clear that with the pH-adjusted water, same pH as the gel. So this is a dopey example of just taking some varnish off with an emulsion. You just wipe the emulsion on, clear it off with a swab, rinse it with the pH-adjusted water, and I'll note that there's still some grime left behind, but you know, it's simple, easy. Could have cleaned this with solvent on a swab, but you know, this works great. And then we also have that issue of not having a solvent that will leach components out of that paint film. We're working more on the surface, and we can always wet that surface with cyclomethicone to really keep that that emulsion on the surface of the paint film and not soaking into it. So, so now's the fun part, the silicon-based emulsion, polymeric emulsion stabilizers. So the opposite of what I just mentioned about PEMulin, xanthan gum, where we put a solvent into that water-based system, is take a solvent-based system that's very low polarity, cyclomethicone, and use a polymeric emulsion stabilizer in that. So we put in, now our favorite is the Shin-Itsu KSG 350Z, or probably as you say over here, 350Z. And we can put in an aqueous phase into that, again, adjust pH, conductivity, all those things we can use to fine-tune that cleaning system into this emulsion and work on a very high, a surface that's very sensitive to water and still use an aqueous system to clean it. So the continuous phase, we use cyclomethicone, either cyclomethicone D4 or D5. And we can disperse our aqueous system into that. And as I say here, control the pH, conductivity, and the option of adding a chelator, because again, these gels are very stable to fairly high ionic materials in that aqueous phase. So this is one diagram of what the cyclomethicones look like. The D4 is a smaller cyclic system. lower boiling point, and the D5 evaporates more slowly, has a higher boiling point. So these silicon-based polymer systems have polar groups. As was mentioned earlier, the Valvasil has polar sections and non-polar sections that form essentially a virtual micelle to hold the solvent in place. The Shin-Etsu KSG 350Z has the silicone system that is compatible with the silicone solvent that we're putting it in, and has these polar domains where we can put water or other high polarity materials into that little cage and suspend the aqueous cleaning phase into the gel. So this is a diagram of what the KSG 350Z looks like. So we have two long polymeric silicone chains bridged by that green ethoxylate chain. So the ethoxylate group is like a non-ionic surfactant. It'll hold the water in place. And we also have extra side chains of silicone and hydrocarbon chains that allow us to put it into mineral spirits or white spirits and all sorts of things. But basically those green squiggly ethoxylate chains will allow us to hold water into that system or other polar materials. Valvasil Plus is kind of what came before the KSG, and it is variably available, not available, or available as Valvasil 125 plus the SF1188A surfactant. But the problem with the Valvasil, it works really well. We all loved it until the KSG came along. But basically, it's a separate surfactant added to Valvasil goo. The goo has the squiggles with the black squiggles in between. That's a aliphatic cross-linking. And then the added surfactant is a silicone linear long-chain polymer with ethoxylate and propoxylate groups attached to it. So kind of by like dissolves like, the Valvasil Plus contains the Valvasil goo and the silicone surfactant, and they're kind of held together lightly, and in the more polar environment that tends to keep them together. But all in all, the KSG 350Z with the incorporated, where the gel material also has the built-in hydrophilic structures, is a much better way to go. So the way we use these materials is we take the Valvasil Plus or the KSG. It's kind of a thick paste already in cyclomethicone. We add more cyclomethicone and stir it up till we get something a little thicker than we want to use in practice. And just like making an emulsion with the Pemulin, we add a water-based system, stir it up, first time, every time we get an emulsion. And we can mix this by hand or with a magnetic stirrer to make this emulsion. But my last slide, and I guess I'm either not seeing the cards about when I'm done, or I missed the cards. Okay. Anyway, the last thing, a handy little tip. If we run the Valvasil emulsion through a syringe with a narrow needle, we get a much cleaner, smoother emulsion. Just comes out the other end, and this is a great way to store it, and you can just dispense the emulsion onto your brush, work it on the surface, clear it with cyclomethicone, and you can put a little piece of tape with what's in the gel, and you're all done. Thank you very much. So anyway, that's my current state of the art, and what's really exciting about this conference is we're moving that state of the art forward. So thank you.